All right, welcome to ECE 203 Lecture 18. Today we're going to continue our discussions of the frequency response of LTI systems or LTI filters. Okay, so what we saw last time, right? We just kind of recalled that one particular way we could describe a filter was by its impulse response. Right? For an LTI filter, that totally characterized the filter itself. And that's just when we input an impulse, right, which is this delta. We input a delta function. The output, which we denote h of n, is called the impulse response, right? And then, of course, general input. If we input some x of n, then the output is the convolution between h of n, right, which is the impulse response, and that particular input signal. Okay, so what we talked about last time, what we introduced, was the frequency response of a filter. And the reason that was interesting was the following. Okay, so say we input a complex exponential at a digital frequency of f hat, right? We input this complex exponential, and then what we get out, of course, is the convolution of that complex exponential signal, that sinusoidal signal, with the impulse response. And we could just factor out, just by kind of taking apart this exponent, writing it as two different exponents, then we could factor out the part that didn't depend on the index of the sum, right? The part that didn't depend on k. And what was that? Well, that was just what's underlined here and written as the input, right? That's this portion. And so we factored out something that was the same signal as the input. So that was interesting because it tells us if we input a complex exponential signal, right? It's a complex sinusoidal signal, then what we get out is another complex sinusoidal signal at the same frequency f hat, right? But scaled now by a complex number. And that complex number depends on f hat. Okay, so the description of the filter we're now going to use is called the frequency response, and that tells us how this complex exponential, how the amplitude and the phase change as a function of f hat, right? Because remember, the frequency of the input signal stays the same. Okay, so in other words, the frequency response tells us that if the input signal is what I have written here, a sum of complex exponentials, okay? So that includes just a regular sinusoid, a real valued sinusoid. So think of these A1, you have A1, A2, A3. These can just be some complex number, okay? And then this complex exponential, that's a signal, right? It's a function of n, and it's a function of a particular digital frequency f hat, f1 hat for this first term. Second term is a complex exponential signal at a frequency f2 hat, and so on. So when we input this sum of complex exponentials, the output of the filter is just the same sum of complex exponentials, except each one has now been scaled by a complex number, and that complex number is the frequency response evaluated at the particular frequency of that complex exponential, right? So this first term, that was at a frequency, a digital frequency of f1 hat, and so it gets multiplied by the complex number h of f1 hat, okay? Likewise, the second term, that was at a frequency of f2 hat, that gets multiplied by h of f2 hat, and lastly, h of f3 hat. So last term was at a frequency f3, and so on. So each h of f hat is just a complex number that tells us how the filter changes the magnitude and the phase of the input sinusoid e to the j 2 pi f hat n, right? This is just a complex valued signal. It's input sinusoidal signal, complex valued, right? Okay, so note that then we can kind of take apart to understand exactly what the filter is doing to signals at different frequencies. We can look at what's what's called the magnitude of the frequency response. It's denoted as the absolute value of h of f hat. It's the absolute value of a complex number, and then it also has some phase. Okay, so there's a little typo here that I just want to correct quickly. And no, this should of course be in the exponent. It should be e to the j times the angle of h of f hat. So we can totally describe the filter by plotting the absolute value of h of f hat and the angle of h of f hat, okay, or the phase of h of f hat, the phase of the frequency response and the magnitude of the frequency response. Okay, I want to talk really quickly kind of about two little notes, two interesting things that we should pay attention to. And that's, we've been talking about what happens when the input x of n is equal to e to the j 2 pi f hat n, right? A complex exponential. But remember, just from Euler's identity, that's just cosine 2 pi f hat n plus j sine two pi f hat n, right? So that's a complex valued input. Usually we've been dealing with real valued inputs. It's just kind of a convenience thing, and that what happens when we input a complex exponential is that the output just gets scaled by a complex number. So let's look at what happens when we just put in a pure cosine. Okay? So what I mean by that is, what happens if we input the real valued signal cosine of 2 pi f naught hat n plus phi? Okay? Well, the output that we get is just scaled. It's another cosine at the same frequency, right? That's the first thing you should know. That for any LTI system, if I input a cosine at a particular frequency, the output I get is just another cosine at that same frequency. Okay, so that's the first thing you should notice. The second thing is that the output has now just been scaled. And what has it been scaled by? Well, it's been scaled by the absolute value of the filter at that particular frequency. Okay? So that's just some real valued positive number that tells us how how much larger or how much smaller the amplitude of the input sinusoid got. But the last thing we have to notice is that the phase also changes, the phase of the output sinusoid. And how much does it change by? Well, it just changes by the phase of the filter evaluated at f naught hat. Okay? So that kind of entirely describes now how, if we just input a simple sinusoidal signal, right, just a simple cosine, we can exactly see what the output of the filter is. If we know the frequency response, all we have to do is say, all right, what frequency was the input sinusoid? We'd say, well, then look at that particular frequency and the frequency response. It tells us how much the amplitude gets scaled by and how much the phase gets shifted by. All right, okay, so that's point one I want to make. The second point is that it's important to see that a lot of times if we're given the frequency response, we can just back out what the impulse response was. And what do I mean by that? Well, let me first remind you guys of the definition of the frequency response. Okay, so that's written right here. And if we have a frequency response whose form is as follows, okay, some number a0, some constant, right, plus a1, and now that a1 is multiplied by e to the minus j 2 pi f hat, and then plus some other a2 times e to the minus j 2 pi f hat times 2, and so on. Well, we can just kind of realize that if we say, oh, I think I know what h0 should be, right? Say, if we set h0 equals a0, right? And if we set h1 equals a1, h2 equals a2, and so on, then say, actually this is the impulse response, because if I look back at that definition for the frequency response, it fits that exactly. So it's kind of a way to do this just by inspection. So see, the frequency response has a particular form. Then compare that to the definition of the impulse response, and figure out that, compare that to the definition of the frequency response, then we can say, well, this has to be the impulse response if it does indeed fit like it does in this example. Okay, so that's just a way to do this kind of by inspection. So we know how to go using an equation from the impulse response to derive the frequency response, but we can also go backwards just by inspecting the frequency response and figuring out which impulse response gave us that particular frequency response. So the next thing I want to talk about is zeros in the frequency spot. And what do I mean by a zero in the frequency response? Well, that's a term you'll hear if you do a lot of signal processing or digital filtering. A zero just refers to a frequency, a digital frequency, at which that particular frequency is totally removed if you pass that signal through that particular filter. So if, as an example, if you look at the plot of a filter, say h of f hat, and if it has points where the filter goes down to 0, right, where the absolute value goes down to 0. So here at what's drawn as minus f naught hat and plus f naught hat, those are referred to zeros. And the way you'd think about this is, it's called a zero because we pass a sinusoid through at that frequency, through that filter. It just gets totally zeroed out. Okay? So how would we design, say we wanted to set out and design a filter that totally removed particular frequencies? Okay? Well, one way we could do that is just by copying this equation that I have. Excuse me, I have here. And why is that? Well, note that in this equation, if I input, say we decide to look at what happens at the frequency f hat equals f naught hat, okay? Then what happens is this first term, this term, this is an f naught hat, and that goes away. That's 0, right, when f equals minus f naught hat, okay? And then the second term, this is also 0, right, at the frequency f equals f naught hat. So then this would be 0. So we end up with two zeros, right? Meaning that at these particular frequencies, minus f naught hat and plus f naught hat, either one of these terms go to 0. Okay? So that's how we start with this, but we can kind of put it in a more intelligible form. Right? So all I'm doing here now is I'm just multiplying things out. Okay, the first term multiplying this term times this term should give me this e to the minus 4j pi f hat. And then the second term and so on, get all these 4 terms. And what I see is I can combine the two middle terms, okay, to give me a 2 times cosine 2 pi f naught hat, right? There's also some phase associated with it, okay, but this cosine thing only depends on f naught hat. So let me continue that on the next page. All right, so rewriting that, we kind of design this filter to have particular location of zeros, meaning that it'll knock out frequencies at a particular location. That frequency that it removed was denoted f naught hat. So we arrive at this expression, and then now we're ready to use that trick that we kind of saw before and just inspect this and say, you know, we can really get this to the form where we can just copy the impulse response. And let me write out the definition of h of f hat, so everyone sees it again. It's the sum from k equals minus infinity to infinity h of k e to the minus j 2 pi f hat k. Okay. So if I set h of 0 to be 1, right, then that gives me this term. if I set h of 1 to now be minus 2 cosine 2 pi f hat, which is this term. Let me write this out here. Say if h of 0 equals 1, if h of 1 equals minus 2 cosine 2 pi f naught hat, right? And if I set h of 2 just to be 1 again, then indeed I can confirm that with that definition, I sum over all k, and of course also say for all the other values of h, set this impulse response to be 0, then I indeed get back that original frequency response. So this is just by inspection I'm able to come up with the impulse response corresponding to this particular frequency response. And then another way to write this out would just be using the delta function, right? And then at the value n equals 1, it takes on the impulse response takes on the value minus 2 cosine 2 pi f naught hat, and at the value n equals 2, it just takes on the value 1. So it's just another way to write the impulse response. So what we've seen is called a notch filter, and it's called a notch filter because it notches out or removes components at plus or minus f naught hat at some particular frequency. So the next thing I want to do is just discuss the endpoint moving average filter and how we can come up with a general definition, find the general frequency response for any m, right? We already did it for the case m equals 2, but let's just leave it as a very general expression now. So the impulse response, right, is just 1 over m times deltas at n equals 0, n equals 1, and so on, a bunch of spikes, right? So that would just look like this. It's the endpoint, the impulse response of the endpoint moving average filter, okay? Dot, 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 all the way out to m. It's got m points. And we can just plug this directly into the definition of frequency response, right? H of f, and now we're going to sum over all k, and all I'm going to do is just plug in the impulse response of the moving average filter, and I'm going to start to evaluate this. Okay, so see right away that any, for any k that's less than 0 or greater than m, impulse response is 0. So I just end up with all these terms. This summing over when k, the value when k equals 0, right, I get this first term. When k equals 1, I get the second term. K equals 2, I get this third term, so on. And I'd sum over all values of k, right? So just add up all of these different things. And then another way to write that, I can just kind of bring that back into a sum, kind of write that in this generic way, is a sum 1 over m from k equals 0 to m minus 1 of e to the minus j 2 pi f hat k. All right, and we've seen this type of sum before, right? Remember, if we have the sum of alpha to the n from n equals 0 to n minus 1, that should just be 1 minus alpha to the n divided by 1 minus alpha. That was something we saw back when we were looking at the DFT. So I'm just using that identity and just plug in down here, and you get this expression that I have written here. Okay, so that's kind of, think of that as well. That's kind of the final answer, but it's useful to plot this and see what this looks like. And what I guess I want people to notice in this plot that I have written below is now, so I took m equals 8, took a particular m, that this expression should have zeros, right? It should go to 0 at any time at the values 1 over m, right? 2 over m, dot, 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 3 over m. And the reason it does that is if we plug in f hat equals 1 over m up here, we end up with the numerator would be 1 minus e to the minus j 2 pi, right? And so that would just be 1 minus 1, which is 0. And then we'd also, if we plug in the value 2 over m, we get 1 minus e to the minus j 2 pi times 2, right? Because the m's are canceling when I plug in f hat equals 2 over m. I get extra 2, and so that's also 1. So these are all the zeros of this filter response, and those are the values here, here, and so on. But again, this moving average filter is a type of low-pass filter, right? So this is a low-pass filter, which we've seen already, what kind of the frequencies that get passed. In here, this is somehow, this width is like 2 over m, right? So the frequencies that get passed depend on the number of points in our moving average filter. Okay, so this is a low-pass filter, and the frequencies that get passed depend on the particular value of m, which is the number of coefficients in the m-point moving